Hello everyone. Hello dear student. See, in this lecture, we are going to discuss a new topic, that is thermodynamic and kinetic requirements of organic reaction. Thermodynamic and kinetic requirements of organic reaction, or we can say any reaction. Okay, so in this topic, we are going to discuss what is mean by thermodynamics of a reaction, what is mean by kinetics of a reaction. That means we have to learn thermodynamics of reaction and kinetics of reaction. So in this lecture we are going to discuss these points related to your syllabus: rate and equilibrium constant, reaction coordinate diagram, transition state activated complex, nature of activated complex, Hammond postulate, reactive versus selectivity, Curtin-Hammond principle, microscopic reversibility, and kinetic versus thermodynamic control of organic reaction. So here in this lecture we are going to discuss somewhat about what is mean by thermodynamics of organic reaction, what is mean by kinetics of a organic reaction, and then we will discuss transition state and activated complex, then what is intermediate transition state, that we will see, then we will see rate and equilibrium constant, then we will see reaction coordinate diagram in more detail. Okay, this what we are going to see in this lecture. Let us start with kinetic and thermodynamic requirements of organic reaction. See, thermodynamics and kinetics. Thermodynamics, which describe a reaction at equilibrium and stability of a product. What is mean by thermodynamics and what is mean by kinetics? So thermodynamics is nothing but which describe reaction at equilibrium. Okay, suppose reaction reaching a equilibrium, that is conversion of A to B or conversion of Y to Z, when this Y is getting converted to Z and when that reaction is coming to equilibrium, okay, or reaching to equilibrium, that will describe by what? Thermodynamics. This phenomenon is described by what? Thermodynamics. And second is what? Stability of product. How products are more stable than reactant, or how reactants are more stable. Okay, this is not, but what? How products are more stable than reactant, this what we can explain on the basis of thermodynamics. So this is what? Thermodynamics. Okay, if product are more stable than reactant, then and then only reaction will proceed further, isn't it? So this is what? Thermodynamics. Now what is mean by kinetics of a organic reaction or kinetics of a reaction? See, kinetics which deals with rate of chemical reaction. Kinetics which deals with what? Rate of chemical reaction. Okay, how faster the reaction is, how slower the reaction is, this will what? Described by kinetics of reaction. So suppose if we consider a conversion of Y to Z. Okay, if we consider what? Conversion of Y to Z, the thermodynamics of reaction tell us relative amounts of Y and Z that are present when the reaction reach equilibrium. Okay, so relative amount of Y and Z that are present when the reaction reach equilibrium, this will described by what? Thermodynamics. Okay, so what is mean by equilibrium? Suppose if we have started a reaction of benzene to nitrobenzene, if we have started reaction of what? Benzene to what? Nitrobenzene at 60 degrees Celsius. Okay, by adding concentrated HNO3 and concentrated H2SO4, by adding, that is nitric mixture. Okay, and if we have heated for 15 minutes, okay, if we have heated for 15 minutes, so in 15 minutes just there is what? 60% conversion of benzene to what? Nitrobenzene. There is what? 60% conversion of benzene to what? Nitrobenzene. So in 15 minutes that equilibrium is reached. Okay, the equilibrium is reached, and that at that equilibrium only 60% molecule of benzene got converted into what? Nitrobenzene. So how much? So that means at that 15 minutes of equilibrium, how much benzene is getting converted to nitrobenzene, this will tells by what? Thermodynamics of reaction. Okay, and how nitrobenzene is more stable, that means nitrobenzene is more stable, hence benzene got converted to what? Nitrobenzene. So this will tell by what? Thermodynamics of reaction. Now suppose if we are carrying out a reaction of benzene to what? Nitrobenzene by nitration, by same nitration, that is by nitric acid and concentrated H2SO4, and at the same time your friend is carrying out reaction of toluene. Okay, that is benzene ring is attached to what? CH3. Okay, reaction of toluene with what? Nitrating mixture to convert a nitrotoluene. Now which will react fast? Toluene will react fast in the nitration or benzene will react fast in the nitration. This will tell by what? Kinetics of reaction. This will tell by what? Kinetics of reaction. That means which species will react fast, which species will react slow. This will we have to learn from what? Kinetics of reaction. So whereas kinetics of the reaction tell us how fast this Y is getting converted to Z, this will come to know by what? Kinetics of reaction. Okay, so at equilibrium how much Y is converted to Z, this will tell by what? Thermodynamics of reaction, and how fast Y will get converted to Z, this will tell by what? Kinetics of reaction. So this is what thermodynamics and kinetics of any reaction we can say. Now, see in this slide we will see kinetic requirement of a reaction, kinetic requirement of a chemical reaction. So what are the kinetic requirement? Okay, so that means for a reaction to become a faster, okay, reaction to proceed a faster rate, to proceed at a faster rate, what are the requirements? What are the kinetic requirement? This is what we have to see. So before that, see there are two definition. One is what? Exergonic reaction, exergonic reaction, and second one is what? Endergonic reaction. Now see what is mean by exergonic reaction? A reaction which proceed with a negative free energy change. A reaction which proceed with what? A negative free energy change is called exergonic reaction, while a reaction which proceed with what? Positive free energy change is called endergonic reaction. Okay, you know delta G. Okay, delta G is equal to what? Delta H minus T delta S. This is what? A equation for a reaction, okay, at equilibrium. So that delta G, okay, delta G is what? Negative free energy change. Okay, if that delta G is what? Minus, negative, okay, then this is called what? Exergonic reaction. Okay, and if a reaction is proceed with what? Positive free energy change, this is called endergonic reaction. Now see delta G, you know delta G is equal to minus RT ln K. Okay, that is also equation. So that delta G, suppose that delta G is negative, then it's what? Exergonic reaction, and if delta G is positive, then it will be what? Endergonic reaction. Many factors must blend together if a reaction is to occur. Okay, if reaction to be a occur, okay, if reaction to be a happen, there should be a many factors, okay, that should be a what? Blend together, that should be what? Blend together, then and then only reaction will occur, otherwise reaction will not occur. That means suppose conversion of benzene to nitrobenzene, when it will take place? Okay, see, reactants must have adequate energy to collide reactant molecule, like that means here we are considering an example of benzene to nitrobenzene. So benzene molecule should have adequate energy to collide. Okay, adequate energy means what? In the form of temperature. Okay, suppose if we are carrying out nitration of benzene at room temperature and your friend is carrying out nitration of benzene at 0 degree Celsius, and one of your friend carrying out reaction of nitrobenzene at 60 degree Celsius. So you are giving the friend which is carrying out reaction at 60 degree Celsius, he is giving what? Somewhat energy, somewhat energy to that benzene molecule, so they will get collide. Okay, they will get energetic and they will what? They will move in the reaction container. Okay, and they will what? Collide. Okay, so reactant must have adequate energy to collide, isn't it? Second factor is what? The reactant must come together, the reactant must come together in a proper orientation favorable for reaction. Okay, so reactant, okay, see, suppose this is a reactant, this is one reactant and this is second reactant, so they must come, okay, come together in proper orientation. Okay, proper orientation, that means suppose they are colliding like this, okay, they are just colliding like this, okay, that will be not a effective collision, this will not be a effective collision. But suppose they are reacting like this, then this will be what? Effective collision. Okay, suppose reactant reacting like this will be what? Effective collision. But suppose reactant are colliding like this, then this will be not a effective collision. Okay, so the reactant must come together in a proper orientation favorable for reaction, that is what? A effective collision. Okay, that means what? They must come in proper orientation means what? Okay, suppose this is a filled orbital of a nucleophile and this is what? A empty orbital. Okay, this is what? A empty orbital of a nucleophile. So this filled orbital and this empty orbital should collide with proper orientation, isn't it? Then and then only there will be what? Transfer of electron from this nucleophile to this electrophile. Otherwise, if collision is not effective, okay, if collision is like this, if collision is like this, if collision is like this, then there will be no transfer of electron from nucleophile to electrophile. Now last point is what? Last factor is what? Sufficient energy must be available. Sufficient energy must be available to break the bonds that undergoing change. Okay, sufficient energy must be available to break the bonds undergoing change. Suppose if any bond is breaking, and that for breaking of that bond sufficient energy must be available. So these are what the factors should be blend together for a reaction to occur. Okay, see, in this slide we will see activated complex and transition state. Difference between activated complex and transition state. Okay, you know transition state. Okay, what is mean by transition states? You have seen transition state in SN2 reaction. Okay, SN2 reaction, that is conversion of methyl bromide to methyl alcohol. Conversion of methyl bromide to methyl alcohol, this is what? A reaction of SN2 reaction. This reaction proceed via what? Transition state. Okay, now we will see what is the difference between transition state and what is the difference between transition state and activated complex. See, activated complex refers to a activated complex refers to a collection of all intermediate molecule formed during the course of reaction. Okay, what is mean by activated complex? Refers to a collection of all intermediate molecule. Okay, so at this stage, suppose when A and B are reacting, when this A and this B are reacting, okay, so initially there will be a formation of this intermediate, later on there is, after some time there is formation of this intermediate, okay, after some time there is formation of third intermediate. So collection of all these intermediate, okay, which are formed at every stages of a reaction, that collection of all intermediate are called what? Activated complex, isn't it? So collection of all intermediate molecule formed during the course of reaction is called activated complex. See, it has highest potential energy than reactant. This activated complex is has what? It has a highest potential energy than reactants. Okay, suppose benzene and nitrobenzene, that sorry, benzene and nitrogen mixture, when they are reacting, so that activated complex which it will form, that will have highest potential energy than reactant molecule. That is, a reactant molecule is what? A benzene. This activated complex, see, it may form the end product activated complex, okay, which is having highest potential energy than reactant, isn't it? So that will form end product of a reaction or can go backward. Okay, that can form a end product of a reaction or it can go backward, isn't it, forming reactants without giving products, isn't it? Suppose this is a potential energy of a reactants. Okay, so when you will have such type of curve, okay, so that activated complex which is located at the top of this curve, okay, so this activated complex may form this end product, okay, this product, or it may form reactant back, isn't it? Now see the transition state. What is mean by transition state? See, transition state is an intermediate of a reaction. Transition state is also a intermediate of a reaction that comprises a highest potential energy, isn't it? This what? It also comprises a highest potential energy. It has highest potential energy than other intermediate structure. This transition state is having what? Highest potential energy than other intermediate structure, isn't it? See, it has highest probability of forming products. Transition state is having what? Higher probability of forming products than forming reactant, isn't it? So transition state can form product very easily than activated complex, we can say. Okay, so these are the what differences between activated complex and transition state. See, here we will see reaction coordinate diagram. Okay, reaction coordinate diagram. Okay, how to draw a reaction coordinate diagram for conversion of A to B or Y to Z, or we may say how to draw a reaction coordinate diagram for the conversion of benzene to what? Nitrobenzene. Let us see how we have to draw this diagram. Before that, we will see the terms involved in it. The mechanism of a reaction describe the various steps that are believed to occur as, okay, see, reactant AB. This is what a reactant AB plus C, isn't it? AB plus C. So see here, this is what a reactant AB. Okay, and we are carrying out reaction of this reactant AB with what? C. Okay, so this AB plus C will get converted into product A plus BC. A plus what? BC, isn't it? So this is what a reactant and these are what a product. So we have converted AB by adding C into it into what? A BC. So reaction coordinate diagram shows the energy changes that take place in each step of mechanism. What reaction coordinate diagram shows? Reaction coordinate diagram shows the energy changes. Okay, how the energy change? Okay, when AB, when this AB and this C, okay, when this AB and when this C will come closer, okay, when they will come closer, then the energy of reaction will rise, isn't it? See, when this AB and C, as they will try to come closer, the energy of reaction will get rise, isn't it? When this reaction will try to happen, isn't it, the energy of reaction will rise. Okay, so a reaction coordinate diagram show energy changes that take place in each of the steps of the mechanism, isn't it? So this what is shown by what? Reaction coordinate diagram. See, in reaction coordinate diagram, the total energy of all species, isn't it? See, in the reaction coordinate diagram, the total energy of all species is plotted against the progress of reaction. See here, this is what a total energy on y-axis, isn't it? On y-axis, there is what a total energy or a potential energy of all reactants. Okay, AB and C. Okay, this is what the energy, total energy or a potential energy of this AB and C. So this total energy or a potential energy is plotted against what? A progress of reaction is plotted against what? Progress of reaction. Now what is mean by progress of reaction? Progress of reaction means what? When AB, this AB reactant and this C reactant, when they will try to come closer to each other, then what will happen? There will be what? Change in the bond length of this AB. Okay, there will be what? Change in the bond length of AB. There will be what? Change in the bond angle of AB. There will be what? Change in the hybridization of AB. Okay, so all these changes are called what? Progress of reaction. All these changes are called what? Progress of reaction. Okay, so how this progress is taking place? Changing bond angle, changing bond length, changing hybridization, how these changes are taking place. Okay, so this is what? Okay, when these changes are taking place at the time, at that time the energy of reaction, okay, the energy of reactant molecule will rise, the energy of reactant molecule will get rise, isn't it? So in a reaction coordinate diagram, the total energy of all species is plotted against the progress of reaction. Now see, a reaction progresses. See, reaction progresses from left to right, isn't it? See, we have shown here reaction AB plus C. So this progresses from left to right, isn't it? Left to right as written in the chemical equations. See here, we have also shown here AB plus C is getting converted to ABC. Okay, so we are on left hand side we are having reactant, and on right hand side we are having what? Product, isn't it? So hence we are showing here reactants on left hand side, and on right hand side we are showing what? Product, isn't it? See here. On left hand side we have shown reactant, and on right hand side we have shown product. Okay, so reaction progresses from left to right as written in the chemical equation. So the energy of reactant, okay, so the energy of reactant is plotted on the left hand side. See, this is what the energy of the reactant that we have plotted on the what? Left hand side, okay, of the x axis. And the energy of product, okay, energy of product is plotted on the right hand side. Okay, this is the x axis, this is the left hand side of x axis, and this is what? Right hand side of x axis. This is the x axis, isn't it? And this is what? A right hand side of x axis. So here this is what the energy of products, and this is what the energy of reactant. Now see, when we will have this AB plus C, this reaction will take place when AB molecule and the C reactants will come closer. At that time there will be what? Change in the bond length, change in the hybridization, change in bond angle. Okay, so at that time the energy of these reactant molecule will get rise. Okay, okay, so initially at initial state free energy of the reactant is what? 0, or it is minimum. Okay, but when they will come closer, the energy of reaction will get rise. Okay, and they will form the transition state. Okay, see, this is what the transition state, the highest energy state on the reaction pathway. This is what the highest energy state on the reaction pathway. Okay, and immediately this transition state will form, that will get collapsed into what? Product. This is what the progress of reaction. Now see, in the continuation of this reaction coordinate diagram, we will see this slide here. Remember that more stable the species, the lower is its energy. Okay, the more stable the species, suppose product is more stable than the reactant, then product will have lower its energy, isn't it? See it like this. Okay, suppose if product are more stable, then product will have lower energy. This is what the energy of reactant, this is what the energy of product. Okay, suppose product are more stable, then it will have lower energy than reactant. And if suppose reactants are more stable, isn't it? Reactants are more stable than the product, then we will have opposite type of reaction coordinate diagram, isn't it? So it will be like this. Okay, so here reactant molecule are more stable than the product. These are what the energy of product, and this is what the energy of reactant. So here energy of reactant is less, that means reactant molecule are more stable than the product. As the reactants are converted into product, the reaction passes through maximum energy state called transition state. Okay, as the reactants are converted to product, these reactants are converted to what? This product. Okay, so this is passing through what? Maximum energy state, and this is called a transition state. This is called a what? Transition state. The structure of the transition state lies somewhere between the structure of reactant. Okay, the structure of this transition state, okay, that is lies between, okay, the structure of reactant and the structure of product, isn't it? So this structure of this transition state, you can say this transition state or this transition state or this transition state, that lies between the what? Structure of this reactant molecule and structure of this product molecule. Bonds that break and bonds that form, okay, bonds that break and bonds that form as reactants are converted to product are partially broken and partially formed in the transition state. Okay, so the bond which is going to be broken See, AB bond is going to break completely, isn't it, when the reaction will occur, and BC bond will form when the reaction will happen. Okay, so these bonds are what broken partially, isn't it? These bonds are broken partially, and this bond is formed partially. BC bond is formed partially and AB bond is broken partially, isn't it? Dash line are used to show partially broken or partially formed bond. Okay, so here we have shown dash line, okay, in between AB and in between BC to show partially broken and partially formed bond. Okay, so this is what reaction coordinate diagram. Okay, so we will have one more slide for this reaction coordinate diagram. Let us see. Now see here, we are having different types of curve. We are having different types of curve of a reaction coordinate diagram, isn't it? See this first curve which indicates that, see what is it? A. This is what? A. So what is this A? A is a fast exergonic reaction. Fast exergonic reaction. What is mean by exergonic reaction? We have seen already. A reaction which proceed with a negative free energy change is called exergonic reaction. A reaction which proceed with what? Negative free energy change is called exergonic reaction. Okay, means negative free energy change when it will be there? When products will have higher stability than the reactant. Okay, when the products will have higher stability than the reactant, then reaction will have negative free energy change, and that will be what? Exergonic reaction. That will be what? Exergonic reaction. See here. This is what initial energy of a reactant, and this is what a initial final energy of a product, isn't it? So see, initial energy of reactant is more than the final energy of product, isn't it? See, when these reactant, okay, when these reactant will come closer, there will be a what? Progress of reaction will take place like this, okay, through a maximum, through a energy maxima, or through a transition state. This reaction will proceed like this. Okay, and here product will have less energy than the reactant. That means product are more stable than the reactant, and this is called minus delta G. This is what? A reaction which proceed with what? Negative free energy change is called exergonic reaction. Okay, so this reaction is having minus delta G, hence this is what? Exergonic reaction, and this reaction will take place at a faster rate. Okay, this reaction will take place at a faster rate. Okay, because what is the driving force for this? Because product are more stable than reactant. Product are more stable than what? Reactant. Now see here, the activation energy is how much? This much, only this much energy is required for a reactant molecule to what? Convert into what? Product. Only this much energy is required. Only this much energy is required. See, this is the energy. Okay, see here, this much is the energy is required, okay, to form product. That means only this much amount of energy is required for reactant molecule to convert into what? Product. Okay, see second B, diagram B, it is also a exergonic reaction. This is also a exergonic reaction. That means here also product are more stable. Product are more stable than the reactant. Products are more stable than the reactant, and this reaction is also having negative free energy change, that is minus delta G. Okay, but see this reaction is what? A slow. This reaction is what? A slow exergonic reaction. Why it is slow? Because here this much amount of energy is required. This much amount of energy is required. This much amount of energy is required for reactant molecule. Okay, so reactant molecule will acquire this much amount of energy to get converted into what? Product. Okay, hence this is what? A slow exergonic reaction, isn't it? So this is completely opposite to this. This is what? A slow endergonic reaction. This is what? A slow endergonic reaction. See here, in endergonic reaction, a reaction which proceed with what? A positive free energy change is called endergonic reaction, isn't it? See here, this is what the energy of reactant molecule. So when these reactant molecule will come closer, then they will have a energy maxima, that is a transition state. then that transition state will get collapsed into what? A product. But see here, these products are having more energy than the reactants. Products are having more energy than reactants. Okay, and this reactant molecule will require this much amount of energy, to get converted into product. Hence, this will be what? Slow endergonic reaction. Okay, and in fast endergonic reaction, the reactant molecule will require just this much amount of energy. Okay, just this much amount of energy to get converted into what? Product. Okay, so this is what? A slow endergonic reaction, and this is what? A fast endergonic reaction. Okay, so I hope we have understood fast exergonic reaction. This is what? Fast exergonic reaction. This is slow exergonic reaction, which are both of these reaction are having negative free energy change. Okay, just what is the difference between slow and fast exergonic reaction? In fast fast exergonic reaction, activation energy is small, while in slow exergonic reaction, activation energy is larger. Okay, and this is what? A endergonic reaction. In fast endergonic reaction, activation energy is what? Small, and uh, slow exergonic reaction, activation energy is larger. Okay, so this is what? Reaction coordinate diagram for all type of reaction. Okay, I hope you have understood this topic completely. We will stop here. Thank you very much. Thank you.